In the previous lecture, we have discussed about the equilibrium electron and hole concentrations, and also we derived mass action law, the relation between the equilibrium electron hole concentration and the intrinsic carrier concentration. Now we are going to derive two important equations, that is N0 is equal to Ni into e raised to Ef minus Ei by Kt, and P0 is equal to Ni into e raised to Ei minus Ef by Kt. These two relations are very important in analyzing the semiconductor. We have to discuss some problems using these equations. So in the previous section, we are going to prove these two equations. So proof. In the previous lecture, we have studied the equation for N0, that is the equilibrium electron concentration, in terms of effective density of states. That is N0 is equal to Nc into e raised to minus of Ec minus Ef by Kt. This is the expression for equilibrium electron concentration in terms of effective density of states. So for an intrinsic material, this N0 can be replaced by Ni. For an intrinsic material, the electron concentration will always be equal to the hole concentration, that is equal to the intrinsic carrier concentration. So that we have already discussed. So N0 can be replaced by Ni, and that is Nc is Nc into e raised to minus of Ec minus Ef can be replaced by Ei. So this is the equation in the case of an intrinsic material. So the above equation is replaced, N0 is replaced by Ni, Ef is replaced by Ei. So these two equations we have already discussed in deriving mass action law. So this can be written as equation 1, this can be written as equation 2. Dividing these two equations, that is 1 by 2, we can get N0 by Ni equal to e raised to Nc get cancelled, so e raised to minus of Ec minus Ef by Kt, the whole divided by e raised to minus of Ec minus Ei by Kt. So this can be raised to x by y, which is e raised to x minus y. So e raised to minus of Ec minus Ef minus Ec plus Ei by Kt. So and this is equal to e raised to minus of Ec get cancelled, and minus on taking we will get, this become plus Ef minus Ei by Kt. So this is N0 by Ni. So N0 by Ni is equal to e raised to Ef minus Ei by Kt. So again, this on cross multiplying we will get N0 is equal to Ni into e raised to Ef minus Ei by Kt. So we have proved the equation 1. So the first equation we have proved, and similarly we can prove the second equation by taking the expression for the carrier concentration, equilibrium carrier concentration for holes, that is P0, which can be written as Nv into e raised to minus of Ef minus Ev by Kt. So for an intrinsic material, P0 will be equal to N0, which will be equal to Ni. So again P0 can be replaced by Ni Nv e raised to minus of this EF can again be replaced by EI, since for an intrinsic material the Fermi level is always in the middle of the band gap. So EF will always be equal to EI minus EV by KT. So again dividing these two equations, we can see that P0 by Ni is equal to e raised to minus of EF minus EV by KT divided by e raised to minus of EI minus EV by KT. So this is on solving, we will get EF minus EV plus EI minus EV. This is EF minus EV minus EI, this is minus EI plus EV. So this will become P0 by KT. So this will become P0 by Ni is equal to e raised to minus, on taking you will get EV and EV get cancelled, and this will become EI minus EF by KT. So on cross multiplying, P0 will become P0 is equal to Ni into e raised to EI minus EF by KT. So these are the two expressions we have to study, that is the expression for N0 and P0 in terms of Ni. So this equation is obtained by considering the equilibrium electron concentration N0 and the intrinsic case, that is N0 is equal to P0, which will be equal to Ni, and on dividing these two equations we will get this equation for N0, and similarly we can derive the expression for P0. So these two equations are very important in doing the problems related to the equilibrium electron and hole concentration and for finding the location of Fermi level. So these two equations are very important. So next we will see a problem regarding the equilibrium electron and hole concentration. So this is the question. A silicon sample is doped with 10 raised to 17 arsenic atoms per centimeter cube. What is the equilibrium hole concentration at 300 Kelvin? Where is EF relative to EI? So this is the question given. So we have to calculate the equilibrium hole concentration only. Here we will calculate both hole and electron concentration. And also we have to find the location of Fermi level. After drawing the energy band diagram of the semiconductor, we have to locate the Fermi level location. So from this question we can see that the sample is a silicon sample. So this silicon sample or the silicon semiconductor is doped with arsenic atoms. So this is doped with arsenic atoms. So we know that if we dope a semiconductor with pentavalent impurities or donor impurities, we will get an n-type semiconductor. So if the doping concentration, if the donor concentration is greater, then the semiconductor will have an n-type behavior. And similarly, a semiconductor doping with acceptors or the trivalent impurities, we will get a p-type semiconductor. So the examples for donor impurities are arsenic, phosphorus, antimony, etc. So these are the examples for donor concentrations or pentavalent impurities. Then boron, aluminium, gallium, etc. These are the examples for trivalent impurities or acceptor impurities. So this we have to understand, or we have to study what are the impurities, donor impurities, what are the acceptor impurities. So a silicon semiconductor doped with arsenic atoms only. So here the doping concentration is arsenic, so that is the donor concentration. So here given the value for donor concentration as 10 raised to 17 arsenic atoms per centimeter cube, or we can simply write it as 10 raised to 17 centimeter raised to minus 3, the number of atoms per centimeter cube. So donor concentration is given, only donor concentration, no other impurities are present in the semiconductor. So this will be an n-type semiconductor. So first in these type of problems we have to identify what type of semiconductor is this. So this semiconductor is an n-type semiconductor. So next we have to check what is the value for intrinsic carrier concentration. We know that the silicon intrinsic carrier concentration at 300 Kelvin is equal to 1.5 into 10 raised to 10 centimeter raised to minus 3. This you have to study because this will not be given in the question paper. So we have to study the value of silicon intrinsic carrier concentration at 300 Kelvin, and this value will always be greater, that is 1.5 into 10 raised to 10 centimeter raised to minus 3. Next we have to check, so here the net doping will be ND, since now Na is added. So otherwise we have to calculate the net doping, ND minus Na or Na minus ND. So whichever greater, we have to calculate the net doping. So if the net doping value is very much greater than the intrinsic carrier concentration, so we have to check this condition. The net doping means the doping difference or the given doping value. If the net doping value is very much greater than Ni, then we can calculate the majority carrier concentration. The majority carrier will be equal to net doping. So this you should have to keep in mind. So if the net doping value is greater than Ni, then majority carrier concentration will be equal to net doping. Here the majority carrier concentration is N0, since the semiconductor is N-type. So we can say the N0, we are first calculating N0. So since the semiconductor is N-type and the net doping is very much greater than Ni, we can say that majority carrier concentration, that is N0, will be equal to net doping. Here the net doping is only Nd. So the value of N0 can be find out with N0 is equal to Nd, and which is equal to 10 raised to 17 centimeter raised to minus 3. So we have calculated the value of N0, and we can calculate the value of P0, or the minority carrier concentration. Or the minority carrier concentration can be calculated from mass action law. That is N0 P0 is equal to Ni square, or we can say P0 is equal to Ni square by N0, which is equal to Ni square means 1.5 into 10 raised to 10 the whole square by N0. N0 is 10 raised to 17. So P0 value can be calculated using the mass action law, that is Ni square divided by N0, which is equal to 1.5 into 10 raised to 10 the whole square by 10 raised to 17. So that value will be equal to, so P0 is equal to Ni square by N0, which is 1.5 into 10 raised to 10 the whole square divided by 10 raised to 17. N0 is equal to Nd, so 10 raised to 17. So this is equal to 2.25 into, so here 10 raised to 20 by 10 raised to 17 means 10 raised to 3. So this is the answer for P0 that is asked in the question, that is what is the equilibrium hole concentration value. So we have calculated the equilibrium electron concentration and hole concentration. N0 value is 10 raised to 17 centimeter raised to minus 3. Also in the question it is asking where is EF relative to EI. So what is the value of EF? Where is the location of EF? So we have to find the location of EF. So since this semiconductor is an n-type semiconductor, we have to draw the band diagram of n-type, that is EC and EV, and EI will be in the middle of the band gap. So where is EF? Since it is n-type, the EF will be closer to conduction band. So we have to find the location of EF with respect to EI. So we have to calculate where is EF with respect to EI. So we have to calculate the difference EF minus EI. So we can calculate the location of EF, the Fermi level equation, by using the formulas N0 is equal to Nc into e raised to minus of Ec minus Ef by Kt, and P0 is equal to Nv into e raised to minus of Ef minus Ev by Kt, and N0 is equal to Ni into e raised to Ef minus Ei by Kt, and P0 is equal to Ni into e raised to Ei minus Ef by Kt. So these are the four equations we have studied in the case of equilibrium electron and hole concentration, that is equations in terms of effective density of states and equations in the terms of intrinsic carrier conservation. So the last two equations are most commonly used since we know the value of Ni at 300 Kelvin for silicon. Similarly for germanium also we will study. So these two equations are very much important. The first two equations are used when the value of effective density of states are used. So here we know the value of Ni, and so we can use any of these two equations. But since it is n-type semiconductor, we will use this equation for N0. So this equation is used for finding out the location of Fermi level. Since the value of Ni is known and the semiconductor is n-type, so we will prefer the third equation for calculating the location of. So you have to study all the four equations. So in this problem we will use the third equation since the semiconductor is n-type and the value of Ni is also known. So the equation is N0 is equal to Ni into e raised to Ef minus Ei by Kt, and from this N0 by Ni is equal to e raised to Ef minus Ei by Kt, and we have to find the value of Ef minus Ei. So taking natural log, we can get ln N0 by Ni equal to natural logarithm of exponential term will be that exponential part, that is taking natural logarithm, this right side become Ef minus Ei by Kt. So from this we can calculate what is Ef minus Ei, which is equal to Kt into ln N0 by Ni. So using this equation we can calculate Ef minus Ei. So this implies Ef minus Ei is equal to, what is the value of Kt? So you should remember the value of Kt. So K is Boltzmann constant, T is temperature. Here temperature is 300 Kelvin. So the value of KT is always 0.026 electron volt at 300 Kelvin. So room temperature value, you have to remember, that is KT value is always 0.026 electron volt. If it is KT by Q, sometimes we will see in problems KT by Q. KT by Q means volt equivalent temperature, that is KT by Q will be 0.026 volt. Here it is KT, it will be in electron volts, 0.026 electron volt. So EF minus EI value, the value of KT is 0.026. So this is 0.026 electron volt. Natural logarithm of N0 is 10 raised to 17 by Ni is 1.5 into 10 raised to 10. So on using the calculator, we can evaluate this value, that is 0.026 electron volt. Natural logarithm of 10 raised to 17 by 1.5 into 10 raised to 10. The answer will always be in electron volt, since the KT value is in electron volt. So the answer will be, on doing it in calculator, the value will be 0.407 electron volt. So this is the value of EF minus EI. So we can see, we can mark this band value in this band diagram. It will be 0.407 electron volt. So all the energy gap should be marked in electron volt. So here the question is, where is the location of EF with respect to EI, and the value is 0.407 electron volt, and this is the band diagram for N-type semiconductor. This is the way we are analyzing the problems relating to equilibrium electron and hole concentration. So any problems you can do with these equations. So you have to remember the value of Ni at silicon and the value of KT. Otherwise you have to study the value of K. K is, for any other temperature you have to study the value of K. K is Boltzmann constant, that is 8.62 into 10 raised to minus 5 electron volt per Kelvin. You have to study the value in electron volt. In joules it is 1.38 into 10 raised to minus 23 joules per Kelvin. So better study the value at 300 Kelvin. So it is 0.026 electron volt. So we will get, on substituting, the value of EF minus EI, and that should be marked in the band diagram. So this is how we are analyzing the problems relating to equilibrium electron and hole concentration. Thank you.